Welcome to Unit 1, Module 4, about atomic theory. The learning objectives for this module include describing the contributions of John Dalton to modern atomic theory, and to describe the evolution of atomic theory. We will begin by talking about early atomic theory, so that we can learn about John Dalton's contributions. Before we can talk about John Dalton, we need to go way back in time to ancient Greece. We're talking 460 to 370 BC-ish, where a few Greek philosophers played an important role in developing atomic theory, particularly Leucippus and Democritus. They proposed that all matter was composed of individual particles called atoms. And in their view, atoms came from just cutting a substance apart until you could no longer cut it apart. Their atoms included various shapes with different properties. For instance, they might have thought that clay atoms were more squishy and cheese atoms were yummy, or apple atoms, had their own crunchiness and flavors to them. It wasn't well evolved. They thought that everything was made out of atoms, including like things that humans perceive, such as sweetness and bitterness. So they thought that there was actually like a sweetness atom. Their ideas were not well accepted, and so Plato and Aristotle, who are very well-known Greek philosophers, they didn't embrace the ideas of Democritus and Leucippus. They thought that substances were composed of various proportions of fire, earth, air, and water. And in Plato's depictions, they had different shapes, like tetrahedrons represented fire and octahedrons represented air. And the ideas of elements being fire, air, water, and earth have pervaded history since this time. And so even in modern times, there's references to these elements, such as Captain Planet and the movie The Fifth Element and the Avatar: The Last Airbender. All of these have these elements to them with the addition of heart and stuff. Also, for very, very long time, millennia, 4 millennia, 3 continents, there's evidence of humans practicing alchemy. Now, it's known as alchemy now. It wasn't necessarily known as alchemy back then on all these different continents, but there's principles are the same. Alchemy involves various different science and pseudoscience and not even science topics together, such as astrology, reading the stars, with chemistry, metallurgy, philosophy, mysticism, medicine. And so it was practiced with some spiritual aspects, but also some practical applications. And so alchemists tried to purify metals, purify substances, and in a large part, they were successful in doing so. And so modern day chemists have some historical names and things that we have to attribute to these alchemists from a long time ago. All these common names that have persisted. Alchemists also wasted a lot of time trying to make a philosopher's stone or an elixir of life, and this was a symbol to represent like the philosopher's stone. To me, it looks like the Deathly Hallows symbol from Harry Potter, kind of, only a little bit different, but circles within triangles within squares to represent the earth, fire, water shapes from the previous slide. The Philosopher's Stone and Elixir of Life was to try to turn lead into gold or other base metals into gold, something more valuable, and hopefully bring immortality. And they were also searching for a remedy to cure any disease. So that lasted for lots of millennia, up until the late 17th century. And that's when Robert Boyle started trying to promote the scientific method. Boyle is still famous nowadays for Boyle's law, which involves a pressure-volume relationship between gas particles. And so if you took Chem 3A or high school chemistry, you might have heard of Boyle's law, which has to do with Robert Boyle, who's trying to pioneer this scientific method. And so he wrote a book to try to say that he was like skeptical of alchemy, and he wanted to promote chemistry, to distinguish between a true science and alchemy. And so this began to discredit alchemy and promote a more scientific study. So we're going to take a brief aside to talk about the scientific method so that we can understand what the difference is between alchemy and actual science. So the scientific method tries to show how scientists build knowledge over time. Science accepts and rejects ideas based on evidence. We can never prove we accept ideas based on evidence, but you can't really prove a positive. So you can't prove something is true, you can just prove something that's not true. And so there's a lot of rejected ideas, and so what we know has evolved to we've made models to try to fit the data that's been collected, and rejected other ideas that do not fit with those observations. So we always make observations and design experiments to test ideas that we have and try to find patterns, trends. Laws also take into account natural laws and phenomenon to formulate hypotheses, and then this gets repeated over and over again to try to refine things, and eventually we can make theories to help explain how the world works. So a lot of times the scientific method isn't presented in such a way that it sounds like first you get a hypothesis, and then as more and more experiments are done, then that hypothesis evolves into a theory and no longer exists as a hypothesis. And then eventually a theory becomes a law. And it's not linear like that. It doesn't start off as a hypothesis, then grow up into a theory, and then grow up into a law. It's not like that. Hypothesis, theories, and laws are like apples, oranges, and kumquats. Fertilizer and water can't change an apple into a kumquat or an orange into a kumquat. These are different things, but they all are ways of scientifically communicating different breadths. So they are all scientific explanations with different scopes and depth. A hypothesis is a proposed explanation for a very narrow set of phenomenon. They are reasoned explanations, not guesses. So, for instance, a specific butterfly species is a hybrid between two other species. That only applies to the specific butterfly species mentioned. It doesn't encompass all butterflies or all species. It's just very specific and very targeted to just that. For instance, if a doctor makes a diagnosis for a patient based on test results, that diagnosis is a hypothesis about what's wrong with that specific patient. It's not a theory, it's a hypothesis about what's wrong with that specific patient. A theory is pretty much as close as we're going to get to a scientific truth fact. It's very broad, and helps try to explain a very wide set of phenomenon. It tries to integrate lots of different laws, lots of different hypotheses, and more importantly, a theory is a model that can help make predictions of things that have not been observed yet. And so theories help frame our understanding of the world because there's so many lines that support it. So for instance, the theory of biological evolution. That doesn't just take into account the specific butterfly species mentioned, it takes into account all these different species over time, and really it helps explain quite a lot. And so in modern day English, the word theory is kind of used as a guess, but in science it's not. Like, you don't say like, oh, I have a theory about why it's so hard to find parking at Fresno City College. No, that's a hypothesis, maybe, or just a random guess. A theory is much more broad. And so the use of the word theory in English and in science is a bit different. A law states observable phenomena that are related. And so how are two things related, or how is anything related? But it doesn't try to explain why. Like earlier we talked about the law of conservation of mass, where matter is neither created nor destroyed in a chemical reaction. It doesn't say why matter can't be created or destroyed. It just says it is. And so now we're going to be talking about two other laws and atomic theory. So John Dalton's atomic theory was first published by John Dalton in 1807. He said that matter is composed of exceedingly small particles called atoms. An atom is the smallest unit of an element that can participate in a chemical change. An element consists of only one type of atom, which has a mass that is characteristic of the element and is the same for all of the elements. There is a caveat there that will get updated later. A macroscopic sample of the element contains an incredibly large number of atoms, all of which have identical chemical properties. So nowadays we know that not all atoms have identical, in an element have identical mass, because we have something called isotopes. But we'll get to that in a little bit. So that's one thing that's going to get updated for John Dalton's atomic theory. But we're pretty good so far. We'll talk about how the atomic theory evolves soon. He also said that atoms of one element differ in properties from atoms of other elements. And a compound consists of atoms of two or more elements combined in small whole number ratios. In a given compound, the number of atoms of each element are always represented in the same ratio. So this one we'll be building on a little bit further. That's going to be our law of constant composition and law of definite proportion. Or multiple proportion is the other law. Law of definite proportions and law of constant composition are the same law. And then he says that atoms are neither created nor destroyed during a chemical change, but are instead rearranged to yield substances that are different from those before the change. And so this ties in that law of conservation of matter. But also tries to explain why. And so it's trying to say, like, we don't destroy matter, we don't create matter, but we can rearrange matter. And so John Dalton's atomic theory was like the first theory for atoms that didn't involve like clay atoms being different from iron atoms. He's trying to say that clay is clay because of its structure and which elements make it up. So he's trying to say that atoms make up all these different substances and we can boil it down into different elements. And so John Dalton came up with 36 chemical symbols based on what was known at the time. And so you can see he used just a circle for oxygen and a circle with one dot in the center for hydrogen and so on. So these were the chemical symbols he used to represent the different elements. And not all of the elements were known at the time, but you can see which elements were known before he even came up with this atomic theory. So these elements have been known in human history for a very long time. I think some of his atomic symbols look way too similar, like zirconium and magnesium. I would get those confused all the time. So let's talk about the law of definite proportion, which is also known as the law of constant composition. In the law of definite proportions, which was mentioned in John Dalton's atomic theory, elements of a given compound always exist in the same ratio. And this means always exist in the same mass ratio. So again, they don't really understand too much about chemical formulas yet, but he's saying that if I went somewhere and I collected carbon dioxide gas from one place and then I went to somewhere else on the planet and I also collected samples of carbon dioxide gas, then they would have the same mass composition. And now we know that that's because they have the same chemical formula and same number of carbon and oxygen atoms in each molecule. But they didn't really know all that back then. So they were doing everything based on mass. And so in this table, you can see that if they grabbed a sample of this compound that weighed 10 grams, then 3.04 grams would be due to nitrogen, 6.96 grams is due to oxygen, and then they can calculate a mass ratio of the more divided by the less, so 6.96 divided by 3.04 is equal to 2.28. So kind of divide each one by the smallest, and then you'll set that equal to 1, and that would be equal to 2.28. If we 2.28. So if we start with something that had 2.28, then that's going to be 1, and then that is 2.28 grams, and that's equal to 2.28. 2.29-ish. Anyway, the same type of principle can be used working backwards. So if you have a 12-gram sample of something, you can work out what mass is due to nitrogen and what mass is due to oxygen. you can go ahead and pause the video and try to figure out how you can work backwards to figure out the mass of nitrogen and oxygen. Are these the masses you got? So how you can figure this out is if you take 12.00 grams and you multiply by your mass of 1 over the total. The total of this is 3, so that's like saying, you know, if you have 1 part water or 1 part oxygen and like 2 parts nitrogen, you have 3 parts total. But really this is 2.28 parts of oxygen for every 1 part of nitrogen equals 3.28 parts overall. So you should end up with 2.35-ish and you take your 12 grams and you multiply by 1 over 3.28. Just double checking myself in the calculator. Yeah. So if you actually work out the mass ratios, this isn't exactly 2.28 from the earlier one. So always use the unrounded numbers whenever you have them. All right. So the law of multiple proportions, which John Dalton had actually published a few years prior to publishing his atomic theory, says that if two elements form more than one compound between them, then the ratios of the masses of the second element, which combine with a fixed mass of the first element, will always be ratios of small whole numbers. And so this is saying that if two elements form more than one compound, then you can kind of figure out relative to one another how much of each element has changed in such a way where it's like a whole number difference. And so this is trying to support that atoms combine in whole number ratios. So for instance, if you have one atom of A and one atom of B in one compound, and then in the next compound you'll find out if you have 1A, you can calculate that you either have 2 B's or 3 B's. And so you can actually figure this out strictly based on masses without knowing molar masses or anything. So for instance, if you had 10 grams of a substance and like on the previous slide, then 10 grams of the substance, you find out that 3.04 grams is due to nitrogen and 6.96 grams is due to oxygen. Then, like on the previous page, you can find out that its mass ratio is 2.28 to 1. So this is the same as on the previous page. But nitrogen and oxygen don't just form this compound, they also form a different compound that has more oxygen for the same mass. So for the same mass of nitrogen, there could also be more oxygen. And now that compound has this ratio of oxygen to nitrogen. So that's 10.42 divided by 3.04 gives you 3.43. And so if we take the ratio of 3.43 to 2.28, we find out that we have 1.50. And that's not a whole number, but that's 1.5. And so that's like 1.5. So you can take that and you can, so if you do 2.28 divided by 2.28, that's 1. And then if you do 3.43 divided by 2.28, that's 1.5. So now you can get rid of this half fraction by multiplying both by 2, and then you end up with they're in a ratio of 3 to 2, or 2 to 3. So between these two compounds, that's your 3 and that's your 2. And so that's saying that for every 2 atoms of oxygen in the first compound, you're going to have 3 atoms of oxygen in the second compound for the same amount of nitrogen.